I'll begin with a word of prayer. Dearly Father, we thank you for this day. Again, thank you for these students. Just asking you to help us to understand a little bit more about Hilbert Spaces and orthogonality, Lord, today. In your name I pray, Lord Jesus. Amen. All right, let me get straight into it. Here we go. Pythagorean formula. I think I stated, I don't think I proved this. This is where we got to. I proved this one? Did I do the induction? I think I did it for, did I do it for n things?
Yeah.
I did? Okay. Well, okay, I'll tell you what. Then I'll start on Bessel's inequality, equality and inequality. So, theorem 3.4.9. I mean, the proof of the Pythagorean thing right before this is trivial. You guys could get it without me telling you about it. So I guess it's better for me to go on to this one. Bessel, equality and inequality. My handwriting, it becomes very unstable at the very top and the very bottom of the board. I've noticed. All right. He says, let x1 through xn be an orthonormal set of... Hey, we're calling them a set now. When'd that happen? Orthonormal. Man, I wish we defined orthonormal set. We never did, though. Orthonormal set of vectors in E with inner product, Lingle-Ringle. Then for each x in E, we have the length of x minus the sum, k equals 1 to n, of the inner product of x with xk in the xk direction, the length of that squared is equal to the length of x squared minus the sum of the inner products of x with xk moduli squared. And the sum k equals 1 to n, inner product of x and xk, sum of the squares of those is less than or equal to the length of x squared. Okay, so the proof. So first of all, since we're an orthonormal set, right, we have that, if we look at the sum of k equals 1 to n of alpha k xk, right, the length of that guy squared is equal to the sum k equals 1 to n of the length of alpha xk, alpha k xk squared, which, because we're dealing with an orthonormal set, is just the sum k equals 1 to n of the modulus of alpha k squared for arbitrary complex numbers alpha 1 through alpha n. So far, so good. So that's the Pythagorean identity. And then I think what he's going to do is just look at this explicitly. So let's do that. All right. So the norm of x minus that sum, k equals 1 to n. And we're just going to label this thing alpha. Alpha k xk, right? That squared is equal to the inner product of x minus that sum with itself, right? And I'll use a different index on the other one. So I'll use j on this other one. J equals 1 to n alpha j xj. Then by properties of inner product, the sesquilinearity, if you will, that's going to give us oh well, that's going to give us, we got x with x, right? And then plus, well, minus x with the sum, alpha j xj. I'll try not to skip too many steps here. I'm going to leave off the sum goes to n, right? So I'm just not going to write that. Minus the sum alpha k xk with x, right? Plus the inner product of the sum with itself. So the first term is exactly the norm of x squared, right? And the second two terms, we can pull the sum out and all right, so I defined this to be alpha k up here, right? And let's think through this. So as you pull the sum out, sum over j, right, and that's going to be alpha bar j, right? Then we have inner product of x with xj. Okay, that's that one. And then we have minus the sum over k of alpha k of xk with x. And over here, I've got the sum of alpha k, alpha bar j, xk with xj. Audric, I don't know if you can hear or not, but there is a bunch of like giggling girls in the other room. So obnoxious. Good grief. Go find a summer camp.
Sounds like ambient noise to me.
That's good. To me, it sounds like I'm in the middle of a summer camp or something. Which would be fine if I was in a summer camp, not a university. All right, so anyway, the point here is that this is literally alpha j. Whereas this over here is alpha. I'm supposed to keep one of these. One of these is supposed to be j. Oh, that's alpha k. Alpha bar k. My bad. It's fine. It's fine. I got lost. And then, of course, this is Kronecker delta. Kj, right? And so what do we get? We get the length of x squared. And there's two of these, right? So minus twice the sum over j. We'll just switch the index both to j's, right? Of the modulus of alpha j squared, because that's these two, right? Both of these collapse down to that.
Oh, yeah.
Because they're both like the...
Oh, you should see K to J.
Yeah, I switched both to j. J is a better letter than k, obviously. And let's see here. And then the other one, again, gives me a sum of alpha modulus squared, right? I'm putting my 1 to n back in. Anyway, so that's from that last term. All right, so what do you got? So we literally then have this. See, because that is the thing in summation, that is the sum of, see that this is equal to the norm of x squared minus the sum of x with xj modulus squared over j. Because that is what the alpha j is by my construction. So there you go. That's Bessel's equality. And I think the inequality follows immediately if we just like do what? How do we get that inequality from the equality?
Oh, you mean just take away the...
I've got the norm of x minus the sum x with xk, xk. So I've got this thing, right? What was the reverse triangle? I think we have this one, right? That's greater than or equal to the absolute value of what? The norm of x minus the norm of that. But this is equal to the length of x. Well, I guess I need to square it, yeah. I don't know. I'm going to sit down. Oh. He just says it follows from it that 0 let me erase this and oh duh. Yeah, I'm working way too hard on this second part because look, this is a norm, right? We have this equality. So of course 0 is less than this, right? And so because, okay. So then we get that we can add this to both sides, and we get that the absolute value of x, the norm of x squared is bounded below by that guy. Yeah. So let's see here. Taking a step back, like what's going on here? So we're not saying that it's necessarily a basis, right? Like it's just an orthonormal set. So I would say like what's going on here is what are you doing here? You're picking off the components of the given vector x, which are in the direction of this orthonormal, the span of the orthonormal set, right? And so if it was a basis, then this would just be equal to x, right? I mean, that would get the whole thing. That would get the whole x back again. But it doesn't have to be a basis, and this is still holding. And this I'm seeing the Graham-Schmidt process in part in play here, because this is exactly what you do. You know, if you have x, which is, if you're trying to orthonormalize, if you have x which is outside of the span of x1 through xn, right? And you want to orthonormalize it with respect to the given orthonormal set. So if you take this if you started with, x not an element in this of the span of, xi, then x minus this, right? Is an element of the span of, span of x1, xn, and x as well. And also, then the set x1, xn paired with x is orthogonal system. And so if you then do the next step of, well, not x, but my bad, I'm not saying, not x there, but good grief, I need to give this thing a name, y. All right, y equals to this thing. But y is the Gram-Schmitting with respect to the given orthonormal system, right? I mean, like, so if the vector's already in the span, it's just going to reproduce the vector again as being as a linear combination across the basis of that subspace. And otherwise, it's giving you a new vector, y, which is orthogonal to the given set, and yeah. So, in part, that's why this is an interesting formula. Let me move on here. He says, note that expression 3.25, which one's that? That was this down here, is minimized. Oh, wait a minute, he did it a different way. Oh, man. Huh. Well, funny. I mean, more power to him. We derived it a different way, whatever, whatever. But if you use his formula, then if you look at his formula and he said it's minimized by taking alpha k equal to that. This choice, oh, yeah, so he's basically arguing for least squares here. He says that oh, good grief. Oh, you better just read it so I don't say it wrong. Let me just write it out. Oh, okay, so the choice alpha k equal to xxk, right? And minimizes the length of x minus the sum k equals 1 to n of alpha k xk squared. Well, you don't have to have the square there, right? So, therefore, it provides the best approximation of x by a linear combination of vectors x1 through xn. Best approximation of x by best approximation of x in, let's just say, the span of x1 through xn. Let's use span. So he says, this property of orthonormal systems is of fundamental importance for many approximation techniques. Okay. All right. He says, if xn is an orthonormal sequence, by letting n go to infinity in 3.24, okay, so this right here is 3.24. He says, let n go to infinity in equation 3.24. What do we get from that? We have that the sum k equals 1 to infinity of the absolute value of the inner product of x with xk squared is less than or equal to the norm of x squared. Oh, what does that mean? Remember our definition of weakly convergent? What was it? I guess it's not weakly convergent. We need to remind ourselves of theorem. Is it 102? That's the definition of weakly convergent. And let's see here. Which one was it? So this shows that weakly convergent sequences in Hilbert space are bounded. Well, okay. Son of a gun. I'm being dumb. I'm being dumb. It's something more. We don't need deep magic for this. we do not need anything sophisticated. This is embarrassing. Okay. All right. Now watch this. It's really, really sophisticated what I'm about to do. We have a series. It is convergent. This proves it's convergent because the norm of x squared is finite value. So we have a convergent series. Therefore, the nth term test tells us the limit as k goes to infinity of the kth term, right? It's equal to 0. And then since we have that the norm, so we have the limit of the absolute values of the squares, so this implies that the limit as k goes to infinity. So by the kth term test to start with, and then by properties of absolute value of a sequence, right? If the absolute value of a sequence goes to 0, it follows that the sequence goes to 0. That's true for real and for complex case, right? If you have the complex modulus of a complex sequence goes to 0, that's true if and only if the real and imaginary parts of the sequence separately go to 0. So this is the absolute convergence of a series, a sequence, the absolute convergence of a sequence to a 0 theorem at play here. But then that is literally weak convergence, right? So then xk goes to x weakly, right? As k goes to infinity. Okay, so wonderful. So orthonormal, so he says, therefore, orthonormal sequences are weakly convergent to 0. He says, on the other hand, since the norm of xn is equal to 1 for all n, orthonormal sequences are not strongly convergent. Let's think about that for a second. But the norm of xn is equal to 1 for all n, right? Oh, sorry, Al. No, it's not.
A little more.
let me do one of these deals. Whoop. It's good? Okay, but well, he's like, okay, but, so orthonormal sequences are not strongly convergent. What would it take what would strong convergence mean? Let's just remind ourselves about that. What does that mean?
Yeah, it's just based on conversion.
That the vector sequence is minus the vector that in the norm goes to 0 and goes to 0.
So we need the norm of xn minus x
Yeah, and that goes to 0.
goes to 0.
Weak is just with you have the inner product going to the
Right. That's the over here was that's the weak convergence. But why is the norm of xn being 1 stop us from having strong convergence?
because by definition it has to go to 0.
Why is that? I thought it has to go
No,
to.
it doesn't strongly converge, right? So it wouldn't go to 0. Right?
I mean, suppose it strongly converges to x. Why is the norm of xn being 1 a problem? Suppose x is not 0. I mean, I don't think a strongly convergent sequence has to necessarily go to 0.
The norm, we haven't induced the norm, which is the square root of the times conjugate. Is that how we call that we get bad thing?
Hmm.
We explicitly state out how we get the norm.
I don't know. This shouldn't be anything too complicated. It's just some kind of like low level. We need to think about the triangle inequality or something like that here to come to terms with this claim. I would think that's my intuition here.
What I'm saying is that if you use the triangle inequality, you get the norm of xn minus the norm of x.
Okay.
Is less than, or yeah, that thing is less than that.
This minus the norm of x, like that,
Yeah,
is less than or equal to this.
yeah. And well, we have 1. You substitute for 1.
Ah, so this is 1
Yeah,
minus the norm of x.
is less than. Let's see.
So apparently the limit, whatever, if it does, that forces, so we must have that the norm of the limit is 1, right?
Yeah.
I mean, I understand why this doesn't happen. What's that?
Did you assume that it's 0?
Well, since this, I'm saying since this can be made less than epsilon for like n sufficiently large, it forces this to have to be 1. Otherwise,
Oh, yeah. It's not going
it would be problematic. Because that goes to 0, that forces this to have to be 0. Otherwise, it can't be reliably put under that. Now, let me look at an example for just a second. So, like an example of an orthonormal system that we saw last time would be what? Like, how about this? E to the INX. That's orthonormal with respect to like one of the, like if you integrate minus pi to pi, right? So if you take a sequence of these guys I can see why it doesn't converge, right? Like I understand this limit, right? Does not exist. So, and I also see that it has modulus 1. I mean, this is an orthonormal system. Well, I got to be careful. I think I have to normalize it to make it orthonormal, right? Because if we go from minus pi to pi, I think I have to divide by like the square root of 2 pi or something, if I remember right. Fine. There. I think that was what it was. Okay, so I understand why that doesn't exist. I don't understand why. It should be something stupid. Why is it that norm of xn equal to 1 forbids the strong convergence of the sequence? Listen, I'm going to go on because I just don't see it. It doesn't pop out at me at the moment. Let's move on here. If you guys think of it as we're going on here, just jump in, yeah? Let's see here. So, he says inequality 3.26. Wait a minute. I thought that was... This is not 3. This is 3.26. My bad. I'll write it again here. So the sum k equals, good grief, k equals 1 to infinity of the absolute value of x minus x inner product of x with xk, absolute value squared less than or equal to x squared. He says that that implies that, yes, okay, we already said this. Sorry, sorry guys, I'm reinventing the wheel at the moment. It says that this converges for all x in E, right? So he says that means that we've got an element of L2. So he says we can say that an orthonormal sequence in E induces a mapping from E into L2. So this means that this sequence, x with xn, is an element of L2. And we write x is squiggle. Let's say it's represented by the sum n equals 1 to infinity of x with xn. So this right here is the generalized Fourier series of x. So if we have an orthonormal sequence of vectors in an inner product space, then we can form the generalized Fourier series of an arbitrary point in the inner product space. And Bessel's equality and inequality give us kind of guidelines for how far. That actually gives us an explicit formula for the difference between the nth Fourier polynomial. I mean, let me go back over here and let me point at things and talk. Oh, you got it? Okay. You're fine.
Where's what you're saying?
Let me move Audric back over here too. You good, Audric?
Yeah, I got it.
Moving you back to the other table. There we go. So I was, so as, this is the nth partial, this is the nth partial Fourier sum. And so as the Fourier series takes on to infinity, this is like the nth Fourier approximate. And this formula says that the difference between the norm of x and the, you can just, the error in approximating x with this Fourier sum is equal to this. The Bessel's equality now is an explicit account of the error in the nth Fourier polynomial for x. And in fact, it is at most what? It's bounded by the length of x, right? So that gives you a bound on the error of the Fourier polynomial. That's it. Well, I was thinking finite dimensionally when I started this story, but seems like it's more than that, isn't it? All right, so let me move along here. I love this stuff. Like, if I just have a collection of the statements that we're trying to prove, like most of these things, you can just sit and, if you know how the inner product works, you can just calculate all this stuff, right? Like you can just calculate it. It's really cool. So this is this generalized Fourier series. Fourier was 1768 to 1830. The scalars that we had over there are the generalized Fourier coefficients. And this set of coefficients gives the best approximation for any finite set of xn's. Now, he says, in general, we do not know whether the series that we just wrote down over there is convergent. However, as the next theorem shows, completeness of the space ensures in convergence. So actually, I'm going to erase Bessel's equality, inequality. Hopefully that won't be a trouble. Well, it's going to be okay. It's going to be okay. That feels, I have this sense of foreboding as I erase this, that like it's going to be the next thing I absolutely need. But we know it, so we'll be okay. So let xn be orthonormal sequence. In Hilbert space. H and let alpha n be be a sequence. I guess it could be any. Be a sequence of complex numbers. Then the series alpha n xn, n equals 1 to infinity, converges if and only if the corresponding series of complex moduli is finite. Moreover, in that case, the norm of the series n equals 1 to infinity alpha n xn squared is equal to, well, okay, so this is unsurprising, but there it is. I mean, it's an orthonormal sequence. Surely the length of this is basically the infinite Pythagorean theorem. All right, so proof. For m greater than k greater than 0, we have the sum n equals k to m of alpha n xn squared is equal to the sum of alpha n squared n equals k to m. Why is that true? Right, by Pythagorean theorem. By the Pythagorean theorem we have that, right? Now why are you interested in this? We're going to have to somehow harness the fact that it's a complete space, right? So you see we're looking at like the tail of the series. This is a typical argument. Okay, so then if the series n equals 1 to infinity of alpha n squared is less than infinity, then we have that this Sm equals the sum n equals 1 to m of alpha n xn is a Cauchy sequence. Let's see here. Why is that a Cauchy sequence? He says from 3.29. Now what is 3.29?
It's just the norm.
It's right here, right?
The norm of this sum.
That's 3.29 right there. Oh.
Oh, is it because it's just complex?
Well, I mean, sorry. So, this is...
Oh, wait, no, it's bounded. If we know by equality, the other has to be bounded. So, the sum of alpha n squared is bounded, is what he said. He said if it's bounded,
Yeah.
then then the sum of the alpha complex numbers with the sequence is the Cauchy sequence, because if it converges in norm, it should converge in. It has to be complete space now. Or no, not complete space, but
Oh yeah, complete space, but Hilbert space was his
yeah,
space.
it's complete.
Yeah.
So, right, this,
We just showed that one. We just showed that one converges, therefore it's complete space, and it converges, it must be Cauchy.
we're getting there. This is finite, right? Which implies that this is, what does that say about this? For this to be, this is what? This is the tail, right? This is the tail of this series. So what you're looking at right here is the mth partial sum of a tail of this series. Therefore,
That should be equal to each other.
yes, these are equal. But my point is that this is finite. That's the whole series, right?
Yeah.
The limit of this as m goes to infinity exists because you're given that this is finite.
Yes.
So that means that this, as m goes to infinity, converges.
Yeah.
Which means that this is a convergent, that this in total is a convergent sequence.
Yeah. And we're in a Hilbert space.
A convergent sequence, therefore a Cauchy sequence.
Yeah.
And since it's a Hilbert space,
All Cauchy sequences
Well,
converge.
Do we even need, yeah.
I don't-
Do we
yeah.
even need Hilbert spaces? Because
Yeah.
Hilbert space, every convergent sequence converges.
Yeah.
Oh, sorry, every convergent sequence is a Cauchy sequence.
right, yeah.
Exactly.
But, I mean, yeah,
No, you said it perfect.
huh?
You said it perfect, yeah.
Yeah, no, I'm just saying, I'm thinking to myself, we have the norm of all that squared, and so, oh, I guess, no, it's still bounded, so, okay, never mind. I think it's good.
So we get that this is a Cauchy sequence. And then he's, like you were telling me, Audric, because it's Cauchy and a Hilbert space, that implies convergence because of the completeness of H.
Is that if and only if though?
Yeah, well, this is the start of the argument. There's the conversely part next. So that implies that this sum n equals 1 to infinity of alpha and xn is equal to x for some x and h, right? So this is, it seems to me this is the reverse implication, right?
Yeah, that's exactly what I'm asking.
So this feels to me like this part of the proof. So the forward part of the proof would be to suppose that the series alpha n xn n equals 1 to infinity converges. Yeah, that's what he says. Conversely, if the series converges, then equation 3.29 again implies the convergence of, okay, so that implies that the sum of alpha n squared n equals k to infinity converges. Well, come on. He says, because the sequence of numbers sigma m, I'm sorry guys, I'm missing something elementary in these arguments and it's bothering me. All right, so that is given to converge. This 3.29 is n equals
Well, if you take the norm and square and convert the series, it still converges.
right.
So if we know that's equal to the alpha n, the sum of the alpha n squared, that sequence has to be the sequence of numbers of that series has to be Cauchy R. I'm not quite sure why it has to be Cauchy R actually.
I mean, by 3.29, this is equal to that in the limit, right? Like,
Yeah, exactly.
so, and if this converges, that means that the norm converges, which then means that the square of the norm converges by our previous theorems. Therefore, I don't see like why he's got it. I don't understand why he's bringing the completeness of the real numbers into play here. Unless he's just like forgetting about a previous theorem that we already have or something. Because it seems to me like this is already saying that this converging means that this converging means that this is less than infinity, right? I mean, which is what we're trying to prove, I think.
Oh, you know what it is? It's the norm.
The norm?
Yeah, the norm has to be a real number, doesn't it?
Yeah.
Yeah.
Therefore, if the sequence we know converges in R, it means it has to be because right, isn't R complete? So
Yeah.
every convergent sequence is Cauchy.
Yeah.
I
Yeah.
think the norm of a complex number, that's a real number.
Mhm.
And that's why he said it's Cauchy in R.
Oh, yeah. Okay, yeah. That makes sense. Yeah, you're right.
I just don't see why we care about it. I don't get it. I mean, I don't get it because like it just seems to be like we are. Who cares if it's Cauchy or not? We're just trying to prove this is less than infinity. So like, doesn't that do this? Why do I have to run through completeness of the real numbers? I don't get it. I'm sorry. My bad. I mean, I agree with you, Audric, about the interplay between complex. Why we talk about real numbers? Because the modulus of the complex number is a real number. You know, fair enough. But he's actually looking at sigma m, which is the sum n equals 1 to m of the squares. So he's looking at, he's doing something different. I mean, I guess he's looking at the sequence of partial sums, right? That's what's going on here.
Yeah.
All right, I'm going to move on since I don't think I'm contributing anything here. What is the takeaway message from this? Is in a Hilbert space, the Fourier series for an arbitrary element does what? Well, not for an arbitrary element, right? If we have coefficients, it's more than that, right? The Fourier series that represents a given element of the Hilbert space faithfully represents the element if only for what? If and only if the Fourier coefficients meet this finiteness condition, right? If you don't have that, then apparently if and only if, right? So that doesn't work. And then he says to obtain 3.28, which is this, it's enough to take k equals 1 and let m go to infinity in 3.29, which is what I feel like I've been doing for every part of the proof. So I must be like not seeing something clearly at the moment. And I'm sorry about that, guys. So he's like, to get this, just let m goes to infinity here. Bam. So yeah. I guess the issue is convergence, right? Like, given convergence of the left-hand side, how do you know you have convergence of the right-hand side? And that's what these arguments down here, which I partially understand at the moment, and you guys probably understand better than I do at the moment, prove. So, his example, he's got an orthonormal set for he's looking at the Hilbert space, which is square integrable functions on minus pi to pi. And he's letting xn of t equal to 1 over square root of pi sine of nt. N equals 1. All right. He says that this sequence is an orthonormal set in H. And if you let x equal to cosine t, you can calculate that the sum n equals 1 to infinity, all right, of xn times xn of t, right? It's equal to the sum, I'm going to do the sum down here, equal to the sum n equals 1 to infinity, 1 over root pi. We've got integrate from minus pi to pi, cos t, sine of nt, dt. And then you got to take that and you multiply it by sine of nt over the square root of pi. And that integral is 0. Why is that?
Is it because the interplay between minus pi and pi? Can you integrate?
Oh, easier than that. This is easier than that. Easier than that.
What's the odd integrand?
This is an odd integrand, right? Because you've got cosines even
And then sines odd.
in sine of any multiple of t. It's an odd function integrated, so it's 0. So this is
If you can split the integral up from minus pi to 0, 0 to minus pi.
yep.
Yeah.
So any integrate an odd function about a symmetric interval of the origin, you get 0. And so the Fourier series here is it's 0, right? And of course that's not equal to cosine t as a function for sure. So apparently, what does that mean? He says the theorem we just half proved, sorry guys, imply that in a Hilbert space H, the series, sum n equals 1 to infinity of inner product x with x and x converges for every x in H. However, it can happen that it converges to an element different from x. That's what this illustrates. So yes, you have a convergent, wonderful, we have a convergent series, right? It's the 0 series. It's not doing a very good job at all, right? It's not doing a very good job at all representing cosine. So just because the Fourier series converges doesn't mean it converges well in the sense of being a good approximation for the given vector, in this case cosine. Does that make sense?
Yeah.
I mean, it is what it is. And still, the Bessel inequality and equation still works out just fine. It's just that the series that was in that formula is just the 0 series. So like the equality we had at the start of class just reduces to like the norm of cosine squared is equal to, the norm of cosine squared is equal to the norm of cosine squared. Yay! True. Who cares? Because it's a 0 series. So there's that. And that brings us to our next definition. If you guys don't mind me doing another definition here. I should try to, what's that? Oh, I need to move you. Yeah. I probably shouldn't have erased what I just erased.
No, we started doing it. Don't worry, it's going over.
Oh, we started late? Yeah, sorry about that. We'll do better next time. Well, we can't go late next time because I got church, but that keeps me,
Does that mean we're going to have a test tomorrow?
oh, the test. Yeah, when should we have the test? So the test should be next Monday.
Don't we have break next week?
Oh, there's break. Oh, I guess Monday after break then. Is that okay, or is it too long, or?
Yeah, I thought you were going to do this week, so I didn't know which ones they are.
Well, yeah, I mean, we could do it this week if you guys would like.
So next week's break for you guys?
Yeah, next week
we'll
is
be off classes.
Yeah, I'm cool with doing it Friday.
this Friday.